Hello everyone. So today's topic is logic families. It includes TTL, ECL, MOS and CMOS transistors. My name is Shivcharan Puri, Assistant Professor, EC Department, Asansol Indian College. Now, because of the advances in microelectronics, the digital IC technology is less than 4 decades has rapidly advanced from small scale integration SSI to medium scale integration MSI, large scale integration LSI, very large scale integration VLSI to ultra large scale integration VLSI. Okay. So this technology and henceforth is now entering giant scale integration GSI. What are those? In these technologies, millions of gates equivalent circuits are integrated on a single chip. The use of ICs has thus reduced the overall size of a digital system drastically. And consequently, the cost of digital systems are also reduced. The power consumption of digital systems because of this has also reduced greatly. Because of the miniature circuitry require much less power. However, ICs have certain limitations too. ICs can handle very large, they cannot handle, very large voltages or currents, and also electrical devices like precision resistors, inductors, transformers, and large capacitors cannot be implemented on a chip. So ICs are principally used to perform low power circuit operations. Okay, so it should be underlined that this should be and rather valid for low power circuit operation. The operations that require high power level or devices that cannot be integrated are still handled by the discrete component as such. So the ICs are fabricated using various technologies, and these technologies are actually, in essence, TTL, ECA, IIL, which uses bipolar transistor, whereas the MOS and CMOS technologies, which uses unipolar MOSFETs. Okay. So most of the digital circuits are constructed on a single chip, which are referred to as integrated circuits. Digital integrated circuits are produced using several circuit configuration and production technologies. Each such approach is called a specific logic family, which we have told in the introduction. Different logic families are described in terms of salient features, internal circuitry, and interfacing of logic families. Some of them are transistor logic, metal oxide semiconductor MOS logic, emitter coupled logic ECL, bipolar CMOS logic, and integrated logic. The classification of digital logic family based on technology. Okay. So based on the fabrication technology, the digital logic family has broadly been categorized as bipolar and unipolar, in which unipolar devices are used, such as MOSFET, which is a metal oxide semiconductor field transistor. It's a unipolar device in which the current flows because of only one type of charge carrier, and that is electron or holes. The example of unipolar family include PMOS, NMOS, and CMOS. Whereas in bipolar logic family, transistors and diodes are used as key elements. Transistors and diodes are bipolar devices in which the current flows because of both the charge carriers, electrons and holes. So hence it is bipolar. So now, based on operations, okay. So now we have talked about technology. Now we will classify it on the basis of operation. On the basis of operation of transistors in IC, bipolar logic families are further classified as you can see the classification. Okay, we'll start from here. You see here. Okay, saturated bipolar logic families and unsaturated bipolar logic families. Now coming to saturated bipolar logic families. In saturated bipolar logic families, transistors operate in saturation region. The speed of saturated bipolar logic family is low. Example of saturated bipolar logic families are, these are all the examples: resistor transistor logic RTL, direct coupled transistor logic DCTL, integrated injection logic IAL, diode transistor logic DTL, high threshold logic HTL, and transistor logic TTL. Okay, we will discuss in brief about TTL, and all other are not discussed. So, coming to unsaturated bipolar logic families. In non-saturated bipolar logic families, transistors operate in active region. The speed of non-saturated bipolar logic families is high as compared to saturated logic families. So the example of unsaturated bipolar logic families are Schottky, transistor logic, emitter, coupled logic. Thus, complete classification of digital logic families is illustrated in the figure below. You can see here, digital logic families is broadly divided into bipolar and unipolar. In unipolar, we are having only PMOS and NMOS and CMOS. In bipolar, we have saturated and unsaturated. In saturated, we have all this, and unsaturated, we have TTL and ECL. Okay, so these are all the broad classification. Now, classification based on level of integration. The logic families can be classified into 4 groups depending on the number of transistors in an IC. You can see here. So these are 2 groups: small cell integration and large scale, medium scale integration. In small scale integration, this type of ICs have number of transistors less than 100 in the IC. Whereas in medium scale integration, it is above 100 but below 1000 transistors on chip. Whereas in large scale integration, the number of transistors in the IC can be 1000 to 10,000. And for VLSI, it is more than 10,000 in a single chip. The characteristic of digital ICs. With the widespread use of ICs in digital system and with the development of various technologies for the fabrication of ICs, it has become necessary to be familiar with the characteristic of IC logic families and their relative advantages and disadvantages. Digital ICs are classified either according to the complexity of the circuit as the relative number of individual basic gates, that is 2 input NAND gates. It would be required to build the circuit to accomplish the same logical function or the number of components fabricated on the chip. The various characteristics of digital ICs used to compare their performance are speed of operation, power dissipation, figure of merit, fan out, current and voltage parameters, noise immunity, operating temperature range, power supply requirements, and flexibilities available. Okay. So these are the broad characteristics of digital ICs. Now let us discuss the speed of operation. The speed of a digital circuit is specified in terms of the propagation delay time. We have discussed this propagation delay time when we were dealing with the flip-flops. It was of immense use. The input and output waveforms of the logic gates are shown in the figure below. We will just be coming to that. The delay times are measured between the 50% voltage level of input and the output waveforms. There are 2 delay times. Let's come to that only. As you can see here. Okay. So as you can see here, 50% of the level. So there are 2 delay time, TPLH when the output goes from high state to low state, and TPLH corresponding to the output making a transition from the low state to high state. Okay. So this and this. The propagation delay of the logic gate is taken as the average of these 2 delay times. So this is how we discuss the speed of operation. Input and output voltage to define propagation time. So this is the input and this is the output. Power dissipation. This is the amount of power dissipated in an IC. It is determined by the current ICC that it draws from the VCC supply and is given by VCC into ICC. ICC is the average value of ICC 0 and ICC 1, that is level 0 and level 1. The power is specified in milliwatts. Next is the figure of merit. The figure of merit of a digital IC is defined as the product of speed and power. The speed is specified in terms of propagation delay time expressed in nanoseconds. Now, figure of merit can be given as mathematically propagation delay time in nanosecond into power milliwatt. It is specified in picojoules. A low value of speed power product is desirable in a digital circuit. If it is desired to have high speed, that is low propagation delay, then there is a corresponding increase in the power dissipation and vice versa. Fan out. This is one of the most important things. This is a number of similar gates which can be driven by a gate. High fan out is advantageous because it reduces the number of additional driver to drive more gates. Now coming to current and voltage parameter. The following current and voltages are specified which are very useful in the design of digital system. As you can see here, high level input voltage VIH. This is the minimum input voltage which is recognized by the gate as logic 1. Okay. Low level input voltage VIL. This is the maximum input voltage which is recognized by the gate as logic 0. High level output voltage VOH. This is the maximum input voltage available at the output corresponding to logic 1. Low level output voltage VOL. This is the maximum input voltage available at the output corresponding to logic 0. High level input current IIH. This is the maximum current which must be supplied by a driving source corresponding to 1 level voltage. Low level input voltage IIL. This is the maximum current which must be supplied by a driving source corresponding to 0 level voltage. High level output current IOH. This is the maximum current which the gate can be sink in 1 level. Low level output current IOL. This is the maximum current which the gate can sink in 0 level. High level supply current ICC. This is the supply current when the output of the gate is at logic 1. Low level supply current ICC 0. This is the supply current when the output of the gate is at logic 0. Now the current directions, as you can see here, it's like this. This is the typical gate. This is the current direction, as you can see here, for the current. Okay. A gate with current direction marked. The input and output voltage defined above are shown in figure for the noise immunity. Okay, we will discuss this. But first, let us know this on noise immunity. Stray electric and magnetic field may induce unwanted voltage, known as noise, on the conducting wires between logic circuit. This may cause the voltage at the input to a logic circuit to drop below VIH or rise above VIL and may produce undesired operation. As you can see here, this is the noise margin. Okay, this one, and you can see this noise margin. Okay. The circuit ability to tolerate noise signals is referred to as the noise immunity, a quantitative measure of which is called the noise margin. Operating temperature. The temperature range in which an IC functions properly must be known. The accepted temperature ranges are 0 to plus 70 degrees Celsius for consumer and industrial applications, and minus 55 degrees Celsius to plus 125 degrees Celsius for military purposes. Power supply requirement. The power sub voltage and the amount of power required by an IC are important characteristics required to choose the proper power supply. Flexibilities available finally. Various flexibilities are available in different IC logic families, and these must be considered while selecting a logic family for a particular job. Some of the flexibility which are available are: number 1, the breadth of the series, type of different logic functions available in the series, popularity of the series. The cost of manufacturing depends upon the number of ICs manufactured. When a large number of ICs of one type are manufactured, automatically the cost per function will be very small, and it will be very easily available because of multiple sources. Wired logic capability. The outputs can be connected together to perform additional logic without any extra hardware. Availability of complement output. Thus eliminates the need of additional inverters. Type of output: passive pull-up, active pull-up, open collector or drain, and tri-state. This can be explained in subsequent sections. We will follow it up. Let us discuss this transistor logic, the first of the family. The TTL stands for transistor-transistor logic. It is a logic family implemented with bipolar transistors, PN junction diodes, and diffused resistors to get the desired logic function. It is the most popular logic family. It is also the most widely used bipolar digital IC family. The TTL uses transistors operating in saturated mode. It is the fastest of the saturated logic families. The NAND gate is the basic building block of this logic family. The TTL logic family consists of several LOSA families or series such as standard TTL, low power TTL, high power TTL, low power Schottky TTL, advanced low power Schottky TTL, advanced Schottky TTL, and fast TTL. Okay, so these are the subfamilies. Two input TTL NAND gate. Let us discuss. Figure below shows the internal schematic of a standard TTL NAND gate. As you can see here, this is the standard TTL NAND gate. Okay, two inputs A and B. Output is here, and this is the two-tempo alignment. Okay. Transistor Q1 is a 2-emitter NPN transistor. As you can see here, it's NPN transistor, which is equivalent to 2 NPN transistor with the base and emitter terminal tied together. As you can see here, the two emitters are the two inputs of the NAND gate. As you can see here, diodes D1 and D2 are used to limit the negative input voltages. Examination of the circuit operation for various possible logic states at the two inputs so we are going to discuss the circuit operation. When both the inputs A and B are high, plus 5 volt Vi, both the base emitter junctions of the Q1 are reverse biased. So no current flows to the emitter of Q1, as you can see it here. Okay, so no current flows here. Okay. However, the collector base junction of Q1 is forward biased, so current flows through R1 to the base of Q2 and Q2 turns on to saturation. Current from Q2's emitter flows into the base of Q4, so Q4 is turned on. Since Q2 is in saturation, the voltage at the collector of Q2 will be low and therefore Q3 will be off. Since Q4 is on, V0 is at logic level, VC is saturation, so the output is at logic 0. Next, when either A or B, you can see here, when either A or B are low, either, what will happen? The corresponding base emitter junction is forward bias and the collector base junction of Q1 is reverse bias. So the current flows to the ground through the emitter of Q1. Therefore, the base of Q1 is at 0.7 volt, okay, which cannot forward bias the base emitter junction of Q2. So Q2 is off. Now with Q2 off, Q4 does not get the required base drive. So Q4 is also off. Transistor Q3 gets enough base drive because Q2 is off. That is, since no current flows into the collector of Q2. All the current flows into the base of Q3 and therefore Q3 is on. The output voltage V0 is equal to VCC minus VR2 minus VBE3 minus VD. Okay, so 3.4 to 3.8 volts somewhere around, which is a logic high level. The operation of the circuit is summarized in table below. As you can see here, now A and B are the two input. So if it is a logic 0 or 0 0, what will happen? Transistor Q1 emitter junction A will be forward biased. Emitter junction B will be forward bias. Transistor Q2 and Q4 will be cut off. Q3 will be saturation and output will be 1, which is as per as the NAND gate output. So in NAND gate, if both are 0 0, okay, the output has to be 1. So likewise we can get all the output, and finally this is the operation of a TTL NAND gate. As you can see here, 0 0 1 0 1 1 1. Any input 1, output is 1. And if both, you can see, if you can see here both input 1, it will be 0. So this is a 2-input NAND gate truth table. Emitter coupled logic. The ECL family is the fastest logic family in the group of bipolar logic families. It has high speed or short propagation delay due to the following reason. It is non-saturating logic. That is, the transistor in this logic are always operated in the active region of the output characteristic. So that's important. They are not allowed to go into saturation. So storage time delays are eliminated and therefore the speed of operation is increased. So in exam, if it is asked that which is the fastest logic family, you can go for ECL. It's come for the objective question also for 1 marks. That is the MCQ. The circuit currents are relatively high and the output impedance is low, with the result that the output capacitance can be charged and discharged quickly. The logic swing, that is the difference in voltage level corresponding to logic low and high states, is kept small, typically 0.85 volt. Now let us talk about the characteristic. ECL family has the high speed with the propagation delay for the order of 1 nanosecond, which is very small. Average power dissipation per gate is large, speed is equal to 40 milliwatt. Worst case noise margin is less, about 250 millivolt. So ECL devices are unreliable to work in noisy environment. ECL devices generally produces an output and its complement, so there is a need of additional inverter as such. Due to the emitter follower stages, the output impedance is very low. Fan out is large because the output impedance is low, it is about 25. The current flowing in ECL circuit remains almost constant, so no current transient are observed and so associated noise is also less. So the advantages and disadvantages of ECL family. First we will talk of the advantages. It is the fastest logic family. High fan out due to high input resistance and low output resistance. Typically fan out is 25. Excellent speed power products. It can provide two outputs simultaneously, example OR and NOR. So no additional inverters are needed. Disadvantages is high power dissipation. Its high speed generate voltage and current transients. Limited logic swings, hence more vulnerable to noise. Now talking about the MOS logic, that is metal oxide semiconductor. This is named as MOS because it uses metal oxide semiconductor filled effect transistors, MOSFETs. In comparison with dipole logic families, the MOS families are simpler and cheaper to fabricate, requires much less power, have a better noise margin, a greater supply voltage, a higher fan out, and requires much less chip area. Very advantageous. However, MOS are slower in operating speed. That's okay. Presently, there are two common type of MOSFETs, depletion type and enhancement type. But enhancement type MOSFETs are widely used. The logic families of MOSFETs can be classified into two categories, PMOS and NMOS. PMOS logic is slow as compared to NMOS logic, hence it is not used in many designs or rather new designs. Symbol of NMOS and PMOS. The circuit symbol of NMOS and PMOS are shown in figure. The arrow in the symbol of MOSFETs indicate either P or N channel. As you can see here, this is the gray and this is the circuit symbol of PMOS and NMOS. Okay. So symbol of PMOS and NMOS is also here. You can see here. This is the NMOSFET. Okay. This is the gate, drain source, drain substrate source, and this is the BGS. And this is the PMOSFET. Okay. CMOS inverter. Figure shows a CMOS logic inverter which is coming. It consists of a pair of N channel and P channel MOSFETs connected in cascade configuration. In the circuit, the P channel MOSFET is on when the input is 0 volt and the N channel MOSFET is on when the input is VDD. Q1 is P channel and Q2 is N channel. When Q1 is on, the output voltage is equal to VDD, and when Q2 is on, the output voltage is equal to 0 volt. Now regarding the circuit operation, when the input is low, Q1 is on and Q2 is off, output is high. When the input is high, Q1 is off and Q2 is on, output is low. The operation of the CMOS inverter is summarized in the table below. As you can see here, A, so 0, it's on, off, and voltage is 1. 1, Q1 is off, Q2 is on, voltage is 0. So advantages and disadvantages of CMOS logic. Advantages of CMOS: low power dissipation, high fan out, high noise margin for higher values of VDD, capable of working over a wide range of supply voltage, Switching speed comparable to those of TTL. High packaging density since most devices need less speed. And the disadvantages: propagation delay is longer than those of TTL, which is typically 25 to 100 nanoseconds. Slower than TTL. Susceptible to damages due to static charge. Latch-ups can take place. Need protection circuitry. So this is all about the CMOS, and we have successfully completed the syllabus of the logic families. Thank you.